Okay, welcome. In the lecture, Flexible AC Transmission System and Power Quality. Up to 19th lecture, we have seen the basic of basic of FACT devices and shunt compensation. Now today, we are going to discuss the static series compensator. Similar to the shunt compensator, we can connect we can connect the FACT devices in the series to obtain the fruitful results. So the static series compensator. In the static series compensator, the learning objectives is to understand the concept of series compensator, then understand the need of series compensator in the power system, and what would be the best location of the series compensator. And it also consists of the control of series compensator, just similar to the shunt compensator. There is a variable impedance type, then converter base type, controllable watt generation in the shunt compensation. Now, before going to the directly to the series compensator, first we will consider a basic need of the compensation. Either it may be a shunt compensation and series compensation. This topic already covered in the introduction of the FACT, but again, because it is very important. Say this is the EHV transmission line. We are having large number of EHV transmission line and very few HVDC lines are there. Suppose in Maharashtra, it is from Chandrapur to Padge, is a 500 kV HVDC line, whereas all the transmission line is a EHV transmission line, extra high voltage AC transmission line. Now, this table contains some system voltage 400 kV, 750 kV, 1000 kV, and 1200 kV. And whereas this is the length of the transmission line, which we have considered, is a 400 kilometer line, then 600 kilometer line, 800, 1000, 1200. So we know that in the two machine system, if suppose there is no resistance is ignored of the transmission line, and two machine system, because our study is restricted to the two machine system, whereas in the practice there are large number of machines are connected. Let this voltage is E1, this voltage is E2, and total reactance is reactance X. Then one may write the equation P is equal to E1 E2 upon X into sine delta. Or let X is the reactance per kilometer and L is the line of the per kilometer. Say here, L is the length of the transmission line in kilometer, whereas X is the reactance in ohm per kilometer, and this is power angle delta. This is the delta. And it is found that from this one may write this is the equation P is equal to E1, E2, L is the length of the transmission line, and X is the reactance in ohm per kilometer. So what would be the curve? The curve is like that. So this is the curve. So this is power P and this is angle delta. Same curve we have considered many times. And we will operate our system much more below than the calculated value as per the conservative criteria. Say this angle is delta, at which the mechanical input is equal to the electrical output, and we keep some margin for the disturbance. Either it may be the fault, either it may be the increase in load and decrease in load. So we will operate our system nearly 30 degrees. Say let delta is equal to 30 degree. Therefore, sine 30 is equal to 0.5. So here this equation is P is equal to E1 E2 Lx into sine delta, and here the delta is equal to 30 degree. Therefore, P is equal to 0.5 E1 E2 upon Lx. So at particular, as per the data of the reactance per kilometer for 400 kV transmission line, 750 kilometer and so on, and length of the line, the handling capacity of the transmission line, power handling capacity, the active power handling capacity of the transmission line has been calculated. Say for 400 kV transmission line and 400 kilometer, it can transmit up to the 670 megawatt. Whereas if the system voltage increases, the same line means the length of the line can transmit 2860 megawatt. For 1000 kV is a 600 megawatt, and for 1200 kV is 8625 megawatt. So it means that very clear conclusion is that if the system voltage increases, if you increase the system voltage, say we are using 132 kV, we are using 220 kV, 400 kV, and one more line has been erected in Maharashtra. It's 765 kV between Chandrapur and somewhere. So it means that if the system voltage increases, the power handling capacity of the transmission line can be increased very fastly. Whereas, what is the limitation of EHV transmission line? If same system voltage, 400 kV, if the length of the transmission line increases, say from 400 to 600, the power handling capacity get decreased from 450, then it is decreased to 335. For 1000 kilometer, 270 megawatt. It means that the length play a very important role in handling the power handling of the transmission line, and hence the stability and transient stability and so on. Why it is? This is because of this denominator, L into X. So as length increases, the reactance increases and power handling capacity get decreased, and at the same time, it will decrease the transient stability limit. So our objective is to increase the power handling capacity even if the length of the transmission line increases. So we want to incorporate a series compensator or series fact devices in the transmission line in such a way that this fact device, series compensator, improve the electrical characteristic of existing transmission line in such a way that it will improve the power handling capacity as well as transient stability, voltage stability, and it also avoid the unwanted power oscillation because of the disturbance in the system. So this is the say objective of shunt compensator. Now this shunt compensator is a static one, therefore it is called as a static shunt compensator. So this is some basic idea related to the EHV transmission system. Now what is the objective? Just it is in the say shunt compensation is ineffective in controlling the actual transmitted power. No doubt with the help of shunt compensator, which is connected in the midpoint when the two machine systems are there. So it is called as a midpoint shunt compensator. Either the shunt compensator may be connected to the near to the load, that is called as a load compensation. But this is used for the reactive power management or the reactive power especially. And it is not, our main objective is not to increase the say transmit more increase in the transmitted power and the control. So this is the one some limitations are there in the shunt compensation which can be overcome in the series compensation. Now second point, it always recognize the AC power transmission over a long line was preliminarily limited by the series reactance, series reactive impedance of the transmission line. we have seen that the power is governed by, say, the voltage is V1 and V2 or E1 and E2 is same. So it is V2 square upon X is the reactance, total reactance of the transmission line into sine delta. So this is play a very important role even if we are connecting the uh, shunt compensation. So we want to reduce this value of X by connecting a series compensator. So it is recognized that the power transmit or the amount of power transmitted is restricted and the length of the power transmission is restricted because of this denominator value X. Now, subsequently, within the FACT initiative, it has been demonstrated that variable series compensator is highly effective in both controlling the power flow in the line and it prevent the stability, improve the stability. So by when we are going to evaluate the, or we are going to say, we will say some, go into the detail of the series compensator, definitely we come across that the not only the power handling capacity, we can very well say control the power and improve the transient stability and voltage stability with the help of series compensator. Now this series compensator, the effect of series compensation on the basic factors like determining attainable maximum power transmission. Definitely, what would be the, if suppose this is the curve for the uncompensated line. If it is possible, we can increase the power handling capacity and so on with the help of, so the maximum power that can be transmitted. What would be the steady state power transfer limit? That is the steady state limit. We can improve the steady state limit. We are operating here somewhere. Now we can operate at the higher angle. So definitely the steady state stability can be increased. Then transient stability, we can improve the transient stability definitely with the help of series compensator. Voltage stability and power oscillation as similar to the shunt compensation. So this is the one. This is the static series compensator. So what is the static series compensator? First of all, we are having without compensation. Line without compensation. This is the sending end. Reactance of the transmission line. And this is the, say, this is receiving end. So sending end VS, VR, and the reactance of the transmission line is X. And from this one, power transmitted P is equal to, if suppose the voltage Vs and Vr is same in magnitude, Vs and Vr is equal to V, then we can write V square upon X into sine delta. So this is the very first point which we have considered from the shunt compensation also. So first is the uncompensated line, and then we will go to the compensation line, compensation of the transmission line. So here, this is for basic idea is that the power is equal to V square upon X into sine delta. Now, the same transmission line is divided into the two parts. So half of the reactance is in the first segment and half of the reactance will be in the second segment. So see, this is the half of the reactance in the first segment and half of the reactance in the second segment. And now a capacitor. Here, the capacitor, say here, in this case, a transmission line and a capacitor, that is a series capacitor, compensator. Now this is our diagram, basic diagram. This is the capacitor XC, capacitive reactance, and this is the inductive reactance of the transmission line, VS, VR. This is VR. Okay. So this is the reactance X. Now it is divided into two segments. So half of the capacitive reactance is here and half of the capacitive reactance is here, Vs, Vm, and this one. So this is the voltage Vm, current in this same phase. And now because of this capacitive reactance, it will inject the voltage in the opposite direction. So the direction of EMF across or voltage across this capacitor and this capacitor will be small. Total reactance drop across the inductor is, suppose this is the inductor, earlier there is nothing is there. So Vx, voltage across inductor or reactance of the transmission line. Now, as this capacitor, the voltage is opposite and therefore the total voltage across the line, voltage drop across the line get decreases. So this is the basic concept as that we are inserting some capacitor or capacitive reactance in series with the transmission line. Now, so voltage across series inductor is equal to Vx twice Vx upon 2, because total, if say this is this one, voltage across the total reactance, and Vc, that is the voltage across capacitor, series capacitor, this result from the increase in line current. As you increase the line current, the voltage is going to increase. And therefore, what is the effective reactance? The effective reactance, X effective, is nothing but the two reactances. This is one reactance, Xc, the second reactance, X. So what is the total reactance and effective reactance? Which is the reactance, inductive reactance minus capacitive reactance. So this is the effective reactance. And this effective reactance is, suppose X is taken as a common, so 1 minus K into X, where K is equal to Xc upon this one. So this, simply it is taken, X is a, say, over there. So we can vary the value of K from 0 to 1. We can vary the value of K. What is the K? K is the degree of compensation. We say, we give the name as a degree of compensation. So degree of compensation is nothing but the reactance Xc upon X. If the reactance, capacitive reactance and inductive reactance, the magnitude and the amount is same, the value of K is 1. Whereas if the value of capacitive reactance is, say, 20%, it's a 0.2, 0.1, 0.3, and so on. So one may choose the value of degree of value of K, that is the degree of series compensation as per the need. So this is the some vector diagram. Now, if you just go to the in the previous, we take the some 1 or 2 equations over there. So from this one may write I is equal to, from this vector diagram, Vs into sine delta by 2 divided by half of the reactance, means effective reactance, S effective divided by 2. Therefore, it is equal to V means we are writing as Vs is equal to Vr is equal to Vm is equal to V. So V upon effective 1 minus K divided by 2 into sine delta by 2. And finally, the value of current I is equal to twice V upon 1 minus K into sine delta by 2. This is the value of current. Okay. Now, what is the power? Up to half of the portion, P is equal to voltage Vm into I. And Vm can be replaced as simply V into I. So we'll see this one. So total current of this one become I is equal to twice V upon 1 minus K into X. This is the effective reactance into sine delta by 2. It is the sine delta by 2. And finally, the power is equal to V square upon 1 minus K into X sine delta. And the reactive power QC is equal to I square upon I square into XC. So this is the equation. So this equation for the reactive power and this equation for the active power. Now see toward our relation. Say for example, without any series compensator or the capacitor which is connected in the transmission line, what would be the P delta curve? It is quite simple, which we have taken many times. It is simple. It's V. This one is the where K is equal to 0. When the K is equal to 0, say for this, P is equal to, what would be the value? What would be the case? P is equal to V square mine upon K is 0. Means there is no compensation over this one. Only the reactance is there. Inductive reactance. So K is 0. So 1 minus 0 into X is X and into sine delta. So see, this equation is similar to the previous equation which we have started. P is equal to V square upon X into sine delta. So this equation implies the without compensation, without any compensation. Either there is no compensation related to the midpoint shunt compensation and series compensation. So this is the curve when K is equal to 0 and P is equal to, say, P maximum into sine delta, where P maximum is equal to, from this one, delta is equal to 90 degree. So it is V square upon X. So this curve, first curve, when K is equal to 0. As soon as we increase the value of K is equal to 0.2, it means that the K, what is the K? It is XC upon X is equal to K. So there is some 20% of the reactor, capacitive reactor is connected in series with the transmission line. So the power handling capacity is increased from this value to this value. So now there is an increase in power. Increase in power transmit by the transmit. This is the capacity has been increased. Now, at the same time, if we just again increase the value of K by some factor 0.4, means there is a 40% of the capacitive reactance is connected in series with the existing transmission line. So now again there is an increase in power transmittability. See, this is the power can be transmitted at a higher value. Means here the P delta curve get improved at the same delta is equal to some particular value. Say for example, if you are taking the delta is equal to some value, say we are taking this one. Earlier we are operating our system over here. So we are operating at delta is equal to 0 initial position. By connecting a series capacitor, the power handling capacity get increases. The power transfer, definitely it is going to increase. And when the K is equal to 0.4, again, the power can be transmit at the same angle. The angle will remain same, whereas it is possible to transmit large amount of power, which increase the steady state limit. So this is the curve indicates that if you are connecting a series compensator, it may be a capacitor, it may be a variable value of the capacitors connected to the in series with the transmission line, the power handling capacity get increases and it will found better control as compared to the shunt compensation. Now this is the power, reactive power, which is shown that K is equal to XC upon 1. And so this is the reactive power. So by this way, we can say that the series compensation play a very important role in modifying the electrical characteristic of transmission line for handling more active power, improve the steady state transient stability, as well as avoid the unwanted oscillations, voltage supports. So there's some comments. It can be observed that and expected the transmittable power rapidly increase with the degree of compensation. See, as we increase the degree of compensation at K is equal to 0, somewhere the K is equal to 0, K is equal to 0.2, K is equal to 0.4, and K is equal to 0.5, K is equal to 0.35. definitely it is going to increase with the degree of compensation. And what is the degree of compensation? K is the degree of compensation, which is the ratio of the capacitive reactance connected in series with the, or series capacitor connected, a capacitor is connected in series with the transmission line. Series compensating capacitor cancel the portion of actual line reactance, and thereby the effective transmission line impedance is reduced as if the line was physically shortened. So what it means that? It means that the effective reactance X effective is nothing but it is the difference of capacitive reactance and inductive reactance. Capacitive reactance and inductive reactance. So it means that for, say, for example, for 400-kilometer transmission line, there is some particular value of the reactance without any compensation. If series capacitor is reduced, it will decrease the effective reactance. It means that virtually we are reducing the distance between two substations, or we are reducing the distance of the transmission line. So it will shorten the physical length of the transmission line. Means physical length means it will indicate that now the transmission line not a 400 kilometer, whereas it is only the 250 kilometers or 300 kilometers transmission line. So there is a virtually we are reducing the length of the transmission line by the series compensation, and therefore it is also called as a line length compensation. An equally valid physical explanation which will be helpful to understanding of converter-based power flow controller. So definitely there is a two type. One is the impedance control, and second is the converter control, switching converter base. So in the series compensation, both type of compensation control over the reactive power. One is the variable impedance type, and second is the converter base type, is we can examine in the later on. So an alternate compensating circuit element may be used as a AC voltage source, which is directly inject the desired compensating voltage in series with the line. So when we are connecting the shunt compensation, this is the transmission line and this is the shunt compensation. Okay, we have seen in the very basic one, it inject the current at the point of connection for the shunt compensation. Okay, shunt compensation. Whereas for the series compensation, in the basic idea or basic one, which we have learned. So this is the series compensator or series fact device. It inject the voltage. It inject the voltage in the transmission line. So this injection of voltage, it may be by the some voltage converter base, which is or switching converter based device, or variable impedance type. It may be a variable impedance type device, controllable device, or it may be a switching converter based device. So similar to the StatCom, StatCom is a switching converter device. So similar switching converter device can be used in the series compensation. So this is for the today's lecture. In the next time we will see the series compensation in the voltage stability, transient stability, and power oscillation. Thank you.